So as we look at the exponential parent function, it goes to the point 0, 1. It has an asymptote at 0, which cannot be crossed. And it either goes increasing to the right. Okay, this one right here. I'll draw an arrow. This is your base larger than 1. If you remember this from last year, we call this exponential growth. This one over here is where your base is between 0 and 1, and we call that exponential decay. Okay. Either one of those, because we can look at both kind of at the same time. What's the range of the function if I stated my range? 0, right? Does it actually touch 0? No, so we use a parentheses open up to infinity. Like I said, the asymptote is at y equals 0. The only other thing we're going to talk about with graphs on these, after we do talk about transformations, is going to be the end behavior. If you remember, we did end behavior when we did parent functions. Do we all remember that was a thing? Yeah. So end behavior. Let's look at the purple graph, because I really can't do both at the same time. Okay? So end behavior, remember one of these statements is talking about the left side of the graph. One of them is talking about the right side of the graph. Okay, so left and right. Oops, both left. There we go. Left. All right, so on the left side of the graph, if I look at the left side, which is over here, where are the x's headed out to as they go that way? Negative infinity, great. As the x's are headed to negative infinity, on that same area of the graph, what are the y's getting closer and closer and closer to? 0. The asymptote, whatever that happens to be. So on the left side of the graph, we are going to negative infinity for x. The y's are getting closer to 0. On the right side, where the x is headed off to the right, infinity. And where the y's headed off to at the same time? Infinity. Also infinity. There we go. Super easy. Okay, good. All right, now all we're going to do to this is add in the fact that we are going to have some transformations. What I need you to notice on each of these is whether the base is larger than 1 or less than 1, so that we know whether it's going up or going down, okay? And then we'll deal with transformations. Some of you may be the type that want to draw the original and then do the reflections up and down off of that. And that's fine, just be a pencil user instead of a pen, right? So on the next page, if I look at question 1, first off, in question 1, what is the base? Okay, the base is 5. Okay, remember when we talked about exponent rules and we said parentheses really matter for exponential stuff? Okay, are there any parentheses in number 1? No, there are not. Therefore, I can only say in this one my base is 5. What does a negative out front do as far as transformations?
Flips it across the axis.
Okay, reflects it across the x-axis. So we know that negative, and I won't write this for all of them, reflects over x-axis. What about this minus 2 in with the x? If it's with the x, which one is it? It's like the left and right, okay? So this moves it right 2. If it was up and down, it will look something like you see here in number 2, okay? All right, so to start off with, I'm just going to graph the original, and then we're going to do the transformations to it. If you want to do it all at the end, that's fine, as long as whatever you're doing is like something you're capable of doing on your own, okay? So based off of this fact, if I was just graphing 5 to the x, okay, because that's like the basic idea of this one. Every exponential function goes to the point 0, 1, increases up to the right because that 5 is larger than 1. Are we all okay with that?
Yes.
Then I have 2 transformations to be done to that. What are they? Reflect it and right 2. Which one gets done first? The reflection first, because it's like multiplying, okay? So first I'm going to reflect this, which makes it go like this. It's a little bit not steep. I'm very bad at connecting the dots on this thing. Kind of like this. And then it moves which way? Right 2. So if I move that 1 point that I have, right 2, does that change my asymptote? Nope, does not, which I haven't drawn in yet. Let's also draw in our asymptote. Where is our asymptote right now? At 0. What's going to move the asymptote? The left or the up and down stuff, right? Because Because it's a horizontal line. Now the rest of that filling in should be relatively easy, right? What would I say about its domain? Negative infinity to infinity are all real numbers. What about a range on this one?
Negative infinity to 0.
Negative infinity up to 0. Just like when we did parent functions, this is not like memorizing. This is just reading it from your graph, right? We said our asymptote stayed at y equals 0. Now let's look at our graph for the end behavior. On the left side, where are my x's headed off to? The x's are going to negative infinity as the y's get closer to 0. Now be careful on the right-hand side. Here's the right side. Where are the x's headed off to?
Infinity.
Infinity as the y's are going to?
Negative infinity.
There you go. Good. Colson's getting this. We're good. Perfect. All right, let's try this a second time. What's my base in 2? 2. Okay, so this is increasing or decreasing? Increasing. All right, so I'm going to draw my basic 1. Basic 1 is going through that point. There we go. Very quick. Nothing like complicated there. Goes through the point 0, 1. What is that negative on the x going to do to it?
Flip it across the y.
Flip it across the y. Okay, so that's going to be the first thing I do. Reflect this across the y-axis, which makes it look decreasing rather than increasing, yes? And then I have one more transformation to be done to it. What is that? Down 3. Now, this is the first time we've had a down, up or down one, right? What's that also going to affect?
Horizontal asymptote.
Okay, the horizontal asymptote is also going to move down 3. So that's going to be in here. The only real point that I have is this one at 0, 1, so I'm going to move that down 3 and connect my dots, looking something like this. All right, so once I know this, I know what's my domain. Negative infinity to infinity, all real numbers. What about a range on this one?
Negative 3 to infinity.
Negative 3 up to infinity. Where's the asymptote at? Y equals negative 3. All right, now end behavior. Remember, let's talk about the left side first. So here's the left side. On the left side, where are the x's headed off to? Negative infinity as the y's are going up to positive infinity. On the right side, here's the right side. Where are the x's headed off to? Infinity. And this time the y's are getting really close to what?
Negative 3.
-3. Good. All right. Do we think we can try one? Maybe?
Not the next.
Well, sure. Why not? What part do I really care about in 3?
1/3.
The 1/3. I don't care about the 2. The 2 is not the base. What does the 1/3 mean for me?
Decreasing.
It's decreasing. So I start by saying, because that base is less than 1, it looks like that to begin with. Now take that and do your transformations and see if you can fill in the blanks quick. All right, now let's check our end behavior. On the left side of this graph, it's going to the left, which means x is going to.
Negative infinity.
And as it's going to negative infinity, it's going up. Therefore, the y's are going to
Infinity.
positive infinity. What about the right?
Let's go from
Out to infinity, y's are getting closer to 2. How we feel about it so far? Good, easy? All right, what's the base in 4?
4.
4. So is it increasing or decreasing to start with?
Increasing.
Increasing. All right, see if you can get the whole way through that one. I have a domain for that one of all real numbers, a range of 3 to infinity, an asymptote at y equals 3. If you think about those fill in the blanks, they're honestly supposed to be like easy points. If you can graph it, just like write down the other things to give you some extra points on those kind of things. So on the end behavior, I would have said as x goes to negative infinity, y is getting closer to what?
3.
3. And as x is going to positive infinity, y is going to? All right. The last 2 exponential functions we'll look at on the next page have this base e. Do we remember e being a thing from last year? Okay, here's the main thing you need to know about e. E is approximately 2.718. For some reason, I'm like, it's ingrained in me to go to 3 decimals on like that and pi and the other things. So not in realistically, do you need to know that number for graphing? No, but the reason I bring it up is this. That means an E graph always starts off increasing, right? Because that's a base that's larger than 1. So it does help you with graphing. It's not that you have to actually know that number right now. It does, though, help you with graphing. So that means in question 5, I look at that and I say, okay, the base is E. Therefore, it begins as an increasing function that goes through 0, 1. What does the negative out front do? Flips it over and then moves it up 5, right? So flipping it over means it goes upside down like this, then move it up 5. Hopefully I'm conveying the order of that properly for you guys because it does matter. If you move it up 5 first and then reflect it over the x-axis, it looks completely wrong. So, yes. All right, so then this one ends up looking like that. All right, what about a domain here? All real. Range would be?
Negative infinity to 5.
Good. Asymptotes at 5. And behavior is?
Negative infinity.
Negative infinity. And y is getting closer on negative infinity to where? 5. Then on the right side, x is going to?
Infinity.
And then y's are headed to?
Negative.
All right. See if you can do 6.
I finally understand the infinity.
Good. So log functions can have that little base. The little base b is what tells us whether it is increasing or decreasing, which looks different. And they will all go through the point 1, 0. These will then have the domain of 0 to infinity because they will have a vertical asymptote at x equals 0. Okay? So a basic log function goes through the point 1, 0, has an asymptote of x equals 0. It's like a sideways exponential. It looks like this. So it's just like the exponential functions on its side. Mm-hmm.
The one with the E that goes to the same point as the long one is just 1, 0, 1. And this one is 1, 0.
Exactly. The range on this one is all real numbers instead of the domain. So that flip-flops from the last one. And then for end behavior, you also have to kind of think about differently as well. Remember, one statement for end behavior is talking about the left side, one's talking about the right side. The right side's kind of the easy one. The left side you actually have to think about. So the left side over here, can you really say that the x's are going all the way to negative infinity?
Yeah.
No, because there's a vertical asymptote. So is it ever going to cross 0? No, the x's as they head to the left get closer and closer and closer to that vertical asymptote, which happens to be where? 0. And on that side, as the x's get closer to 0, the y's are going down, which means they're going to negative infinity. Now the right side, like I said, easier. X's on the right side are headed off to infinity, and y's are also going up to infinity. Okay, so now we're just going to practice a few transformations with these, and then we'll be done with graphing. All right, so on the back here, again, what we have to identify with the base is just whether it's a number greater than 1 or a fraction between 0 and 1, which isn't as common with logs, so a lot of them are going to have bases that are larger than 1. In this case, number 1, we have a base right here that is larger than 1. Therefore, our log function is going to be increasing out to the right. Okay? What is that transformation going to do?
Right 1.
Right 1 and
Up 2.
up 2. Okay, so I take that point that was at 1, 0, and I move it right 1 up 2. So here it is. Which one of those two moves the asymptote this time? The right and left is going to move it, because think about a vertical line. If you move a vertical line up and down, it really goes nowhere, right? So the right one is what moves the asymptote, right 1. And when I connect my dots, my log function is increasing up to the right. What's the domain on this one?
1 to infinity.
1 to infinity. What's the range on this one?
All real numbers.
All real numbers. Where is my asymptote on this one?
X equals 1.
X equals 1. And now let's think about the end behavior. On that left-hand side, what are the x's getting closer to? 1. As the x's are going towards 1, the y's are going towards? All right. And on the right side, as the x's are headed off to? The y's are also headed off to? Oh, there you go. see if you can make, or give number 2 a try and see where you go from there. The base on this one is what number? 4, which means it's increasing still. Yes? So we'll practice a couple of the log graphing ones on our homework now. When we are switching between the forms, the little loop, I don't know what else to call it beyond the loop trick. You basically draw a loop around this. The first thing goes first in the exponential. The second thing goes second, and the third thing goes third. You know, oddly enough, it goes in order. So when I write that in exponential form, it goes, the first thing is base 4 to the second power equals 16. So if you can just follow that loop around in order, you use the numbers in that order, okay? So similar for this one. If I rewrote this in exponential form, it would say what? B to the 5th equals 7. Now 3 does not have a base written, but we all just discussed log, or ln is the same as log base what? E. So if you need to think about there being a little base e down here, it would then say what?
E to the 3rd
equals c. We all feel like we can switch into exponential. The good news about the loop thing is that it works both ways. If you do that loop on a log, it goes into exponential. If you do that loop on an exponential, it goes into a log. So if you use that in the second part, same kind of idea, only you lead off with log base, the first thing. So you say log base, a what number? 2 of what? 1/8 is equal to the third thing, -3. I know, isn't it kind of nice? You'll stop having to even write it because you'll just think of it in that order. So the second one would be log base what? 10. I don't care if you write the 10 or if you don't write the 10. That's totally up to you. So log base 10 of what? 1 is equal to? 0. Now what I do care about is number 6. When we use this, in my mind, I think log base what? E. Well, what is log base E? ln. You do need to write ln. Of 12 is equal to A. Now, like I said, it feels like we're just playing with numbers on that. Next class, we'll talk about using that to solve. Because once you can switch forms, you can sometimes get a variable by itself. And it very much helps you. The other thing that it helps me with is actually evaluating logs without a calculator. Some of you are good at this because you can already think about them in exponential form, and that's great. If you're not good at these, because let's be honest, no one taught us to think in logs. Like, we're not taught that. We're taught to think in exponents. So for each one of these, I just kind of put in, and again, if you don't need to do this to rewrite it in the other form, don't do it. But this is just me, so just use it if it helps you, okay? If you don't know what this is equal to, I'm just going to say it's equal to x, so that I have a placeholder there. And then I'm going to take this, and I'm going to rewrite this in exponential form, so that it says what? 3 to the x is equal to 81. And like I said, you're not taught to think, I wonder what log base 3 of 81 is, but you do know 3 to what power gives me 81? 3 to the 4th. Okay? And if you can't think about that, you are perfectly fine to think to yourself, okay, 3 squared is 9. 3 to the 3rd is 27. You know, keep multiplying up through them. Okay? So go ahead and see if you can try 8. All right, so number 8, rewritten as an exponential, says 8 to what power equals 2? Are we familiar with what kind of powers make things smaller? Fractions, right? So 8, can we square root 8? No, so the 1/2 wouldn't work. What can we do with 8? Cube root it. The cube root of 8 is 2, right? What's a cube root as an exponent? 1/3. Now, if that does not feel real comfortable to you, next class we're going to learn the common base method, where we say, okay, 8 is 2 to the 3rd power. Keep the x. This is 2 to the 1st. Cancel the common bases and solve what's left. Still gives you 1/3. Okay? That's the solving that we're going to learn next class. But we will get better at it. Okay? Yes, sir. No, -3 would put it on the bottom and cube it. But we're going to get to negative exponents here in a second. Okay? I'm going to skip down to 10 real quick. And I'll come back to 9 for a good reason. 10, if I rewrite, it goes 5 to what power gives me 1? Well, what exponent makes things 1? 0. Good. I know, all the exponent rules that we love so much. Let's see, which other ones do I want to talk about? All of them, but just in what order? Speaking of negative exponents, let's look at 9. In order for me to think about 9 properly, I do have to rewrite this using negative exponents. If an e to the 4th made it onto the bottom of the fraction, it really was e to what power? The negative 4th. Now, why do I bring that up? Because if anything that you remember from exponentials and logs last year, what do we remember about ln and e? They cancel each other out. Okay? So ln and e are inverses of each other, and they cancel each other out, and you are left with the exponent right there, which happens to be negative 4. It works very similar to question 11. If you have log base 5 of 5, do we remember what happens with those?
Cross them out.
All of that cancels out too, which leaves you what? 8. Okay? Remember those, maybe? No? It happens. We'll see. Log base 5 of 5 is essentially 1, which just leaves you like the 8. That's it. Okay. Yeah. All right, let's move down to 12. I know I'm kind of skipping around. Ooh, actually 14. 14 has to do with the same ones. I need to rewrite this. That's fine. If there's no base written in 14, what's the understood base? A 10, right? So that's log base 10 of, how do I write 10, the square root of 10 with an exponent? 10 to the 1/2, right? Now this looks a whole lot like the one we just talked about, right? Log base 10 of 10, what happens to that? Cancels, which leaves us what? 1/2. All right, and then save the last 2 for the hardest ones, right? 12 written in the form of exponentials. What does 12 look like as an exponential? 9 to what power equals 1/3? This is where we always struggle a little bit to think about what exponent does this. Well, first, 9, what exponent would take a 9 and make it a 3?
3. Oh, 2.
3 squared does 9, but 9 to the 1/2 does 3, right? Because it's like the square root of 9. But now it's not just a 3, it's a 1/3. So what puts it on the bottom?
Negative.
A negative. So this is where we get a negative 1/2 from that. The 1/2 square roots the 9. The negative puts it on the bottom of the fraction. This is where some of you are going to go to that common base method and think that's going to be easier. So that same idea, 9 is 3 squared. Keep the x. 1/3 is the same as 3 to the negative 1 power. Then in common base method, you can cancel the base 3's and solve what's left here. 2x equals negative 1. Therefore, x is negative 1/2. So some of you will feel better about that as like a solving equation. Okay? And then 13 is the last one we're thinking about as exponents. If I rewrite it in exponential form, it says 4 to what power equals negative 4? What kind of exponents make a base negative? A negative exponent makes it into a fraction. A fraction exponent is like a root.
Imaginary.
None. That's close. There are no exponents that make a base negative.
No.
So what this means is you may not take the log of a negative number. This is no solution. Okay? And if you want to make yourself a note, may not take the log of a negative number. Alrighty? Almost. I know, almost. Last part of today is our log properties on the next page. Okay? Several of them we've talked about already, like 1 and 2. If this base and this base are the same, everything cancels out except that leftover m at the end. Same thing with 2. Log base b of b cancels out, leaves you the exponent as the final answer. Okay? Now the other 3 rules are expanding and condensing rules. Do we remember doing expanding and condensing last year?
Yeah.
Yes-ish. Okay. Now, these are rules that work two different ways. Okay? So, one of them is that you can take a log and split it up into two pieces, which is what this direction is. The other way is to take two logs and condense it back to one, which is what we're going to use for solving. What you really need to know about these rules is that in number 3, multiplication expands to addition, or addition condenses to multiplication. Okay? In number 4, what's that one telling us?
Division and subtraction.
Division and subtraction go together. The log of something divided goes to two logs that are being subtracted, or vice versa. But they go both directions. The last rule that we have to talk about is number 5, and that's if you have an exponent on a log, you can bring it down to the front of that log as a coefficient. Okay? Now, several of these go very quickly, like in number 1. What do you think happens with 5 to the log base 5? It cancels. Leaves me what?
18.
Good. In 2, what happens with log base 3 of 3? Cancels. What does it leave me? X minus 2. In 3, what do we know about ln and e? Cancel, which leaves me?
3t.
All right. And one more nice easy one. Log base 5 of 5.
Root 3.
Root 3 left. Okay, now what you can't do is what you want to do in number 5. How many logs do I have in number 5? 2. You may not start canceling that 4 to the log base 4 until you only have one log in your exponent. Okay, and this is the beginning of solving for us. So what we're going to do in 5 here is just take a look at this part. What I'd like to do is I'd like to take that part and condense it down to one log so that I can cancel. So the first thing I look for when I'm condensing is any numbers out front of logs. Do I have any numbers out front of logs? I have that too. Anyone remember what we just said you could do with those numbers out front?
Exponent.
Bring it back as the exponent. So that 2 goes back as the exponent of 3. Okay. We all okay with that?
Yes, ma'am.
Then I notice that these 2 logs are being added. What did we say we can do with 2 logs that are being added?
Multiplication.
Take them together and multiply the pieces. So what that means is I'm going to have 1 log base 4, and what am I actually multiplying here? 6 and 3 what?
Squared.
3 squared, right? So 6 and 3 squared is 6 times 9, or 54. Yes? Now I have it down to 1 log. Now what am I allowed to do with the 4 log base 4? Cancel. There. 54 being my final answer.
That's so easy.
All right, last step on the last page and we'll be done. All right. Condensing in 6. Same idea that we just did in that exponent. First things first, is there any number in front of a log in number 6?
1/3.
Where does that go back to?
On to 27.
On to 27. Now, what is a 1/3 exponent the same as? It's like a
Cube root.
cube root. What is the cube root of 27? 3. So now I have this log base 2 of 3. Then what do our log rules tell us we can do with minus signs? Divide. Now, we don't lose the whole log. It just is 1 log out front, and you divide the pieces. So what is 48 divided by 3? 16. Now, because of that first page we talked about, we don't even necessarily stop here. Because could I switch this into an exponential and simplify it? Yes. 2 to what power gives me 16? The 4th. Therefore, this whole thing simplifies to one number. It is nice and easy. Okay. All right. On 7, we've got variables. Let's start inside here. Okay. I have 3 logs. You don't really have to do this in steps if you really understand what's going on with them. The first 2 logs are being added, which means when I put them together, what do? Multiply. So I keep the log base b and I multiply m times n. The third log is being subtracted, which indicates what? divide. So where do I put the P? On the bottom. And last but not least, what does the 1/2 out front mean for us? It's like a square root, but it applies to that whole thing. So when I take it back to the back part of it, the square root goes over this whole thing rather than just one piece. Okay? So 1/2 exponent as a square root goes back there. And then last two. Expanding is just going the opposite way. So in question 8, how many separate parts do you see? 3. I see an x to the 3rd, I see a square root, and I see a z to the 5th, right?
Yes.
What's happening with the first 2?
The multiplying.
So when I expand it, I split it with a plus sign. The last one is being divided, which means it goes with a minus. So I'm going to separate this all at once and say, okay, log of x cubed plus log of. Now, are we okay with me doing y plus 5 to the 1/2? Yeah? Exponent. And then, because that z to the 5th is on the bottom, I subtract log of z to the 5th. So I split it all up all at once. And then what are we allowed to do with exponents? Put them in the front. So that 3 goes out front here.
If we don't put it in the front of the wrong.
In an expanding problem, it would be wrong to do that if you don't put them in the front. Yep. So you bring each of those, whoops, not that. That's a big eraser there. All right. And we get rid of the exponents on each one of those. Okay. Last but not least, how many pieces do we see inside the parentheses in 9? We have 2, yes? We have an x, and we have the square root. They are being what? Multiplied. So when I separate them, they become added. X and ln of 1 plus x squared. What exponent do we put on that? 1/2, because it's a square root. What's the last thing we can do with any exponents? Now, that only applies to that 1/2, not the x squared, right? Because that's not on the whole thing. It's just on the inside. So that 1/2 comes down here, but we don't do anything with the x squared. Okay? All right. So now, we did the graphing. We did all this, which is a lot for a day, and I appreciate you sticking with me on that. For the homework, we did most of the graphing already. And for the rest of it, I would like to just go with the odds. Okay? After the graphing, odds.